The paper explores the impact of additive Gaussian noise on the spatio-temporal dynamics in ring networks of non-locally coupled chaotic maps. The local dynamics of network nodes are described by the logistic map, the Henon map, and the Ricker map. The authors construct 2D distributions of the probability of observing chimera states in terms of the coupling strength and the noise intensity for several choices of the local dynamics parameters. They show that the chimera states demonstrate a resonance-like dependence on the noise intensity and the coupling strength. Moreover, there is an optimum noise level at which the interval of the coupling strength within which chimera states are observed with a high probability for a large number of different realizations of randomly distributed initial conditions and noise sources. This phenomenon demonstrates a constructive role of noise in analogy with the effects of stochastic and coherence resonance and may be referred to as chimera resonance. In the context of a ring network comprising non-locally coupled discrete time systems, this research explores the phenomenon of chimera resonance, which is induced by additive noise. The network consists of three different types of chaotic maps: logistic, modified Ricker, and Henon maps. The system's equations are defined in the paper, with the addition of a noise term representing the influence of external disturbances. The study focuses on the role of noise in enhancing the emergence and observation of chimera states within a wide range of non-local coupling strengths. This effect, referred to as chimera resonance, parallels the constructive role of noise in stochastic and coherence resonance. The paper presents a quantitative measure for assessing the network's dynamics through the cross-correlation coefficient, which indicates the degree of correlation between the first and other nodes in the network. This coefficient takes values between 1 and +1, with 1 and +1 corresponding to complete antiphase and in-phase synchronization, respectively, and 0 indicating desynchronization. The results show that the presence of additive noise can induce the appearance and observation of chimera states in the studied networks within a sufficiently wide range of the non-local coupling strength. This sigma interval can be the widest at a certain optimum noise level at which chimera states are observed with a high probability for a large number of different realizations of randomly distributed initial conditions. This phenomenon demonstrates a constructive role of noise in analogy with the effects of stochastic and coherence resonance and may be referred to as chimera resonance. The paper also presents a detailed analysis of the network of non-locally coupled logistic maps, where the spatio-temporal dynamics are studied for a set of 50 to 100 different realizations of randomly distributed initial conditions. The study reveals 4 distinct regions in the alpha L, sigma parameter plane, corresponding to coherent and incoherent dynamics, snapshots with profiled discontinuities, and chimera states. The regime diagrams reflect qualitative similarities, but there are some quantitative differences in the boundaries between the regions with coherent and incoherent dynamics and between the regions with coherent dynamics and snapshots with profiled discontinuities. In a network of non-locally coupled logistic maps, the interplay between the local dynamics parameter alpha L, the coupling strength sigma, and the additive noise intensity d significantly influences the emergence and stability of chimera states. The probability of observing chimeras in the sigma d parameter plane is non-zero for certain intervals of sigma, with a resonant-like shape, indicating an optimal noise level that maximizes the probability of chimera formation. The introduction of additive noise can either enhance or suppress the emergence of chimera states, depending on the specific parameter values. For instance, in the presence of weak noise, the spatial profile of the network can be smoothened, leading to the formation of incoherence clusters and thus chimera states. However, further increasing the noise intensity can lead to the destruction of chimeras and the emergence of incoherent dynamics. The analysis of the temporal dynamics of the network elements reveals that within the coherence region, the nodes can exhibit regular or irregular behavior in time, while in the incoherent spatial structure, the nodes demonstrate periodic and irregular dynamics with period doubling bifurcations as the coupling strength increases. In the regions of snapshots with profiled discontinuities and chimera states, subsequent period doubling bifurcations occur in time as the coupling strength decreases. The probability distributions for the observation of chimera states in the sigma d parameter plane for different values of the local dynamics parameter alpha L show that the width of the noise intensity d range of a non-zero probability changes as the coupling strength increases within the sigma interval corresponding to the observation of chimeras with a high probability. There is an optimal noise level at which the width of the sigma interval is the largest, demonstrating a constructive role of additive noise, which is typical for the phenomena of stochastic and coherence resonance. This peculiar influence of noise on the observation of chimera states may be called chimera resonance. This resonance-like effect is not unique to the dynamics of the noisy network of non-locally coupled logistic maps but is also realized in networks of other chaotic discrete time systems in the presence of additive noise. The research discusses the phenomenon of chimera resonance in networks of chaotic maps, focusing on the logistic map network. It explores how the introduction of additive noise affects the probability of observing chimera states. The study shows that with low noise intensity, the probability of chimera existence can increase to almost 1, and there's a specific noise intensity range where the probability is maximum. The coupling strength also plays a crucial role, with certain values leading to a wider range of high probability. The analysis includes numerical simulations for different coupling ranges, demonstrating the non-monotonic dependence of the coupling strength on noise intensity. The results indicate that there's an optimal noise level for each coupling range, resulting in the largest width of the sigma interval corresponding to the maximum probability of observing chimeras. This phenomenon is further verified in a network of non-locally coupled Henon maps, showing similar patterns. The findings highlight the complex interplay between noise and coupling strength in these systems, shedding light on the conditions for optimal chimera resonance. In the context of networks of non-locally coupled chaotic maps, chimera resonance is a phenomenon that emerges as a result of varying the local dynamics parameter and the coupling strength. This paper explores this phenomenon in 3 different networks: logistic maps, Henon maps, and modified Ricker maps. The study reveals that each network exhibits 4 typical dynamical regimes in coherence, snapshots with profile discontinuities, and chimera states. For the logistic map network, the probability of observing chimera states is investigated in the presence of additive noise. The results show that the probability distribution can be either unimodal or bimodal, depending on the value of the local dynamics parameter alpha. The bimodal distribution is associated with 2 distinct routes for the transition from incoherence to coherence, one involving a coherent window, and another without it. The existence of a coherent window is also observed in the Henon map network, where the network demonstrates periodic dynamics in time with periods t=4 and t=8 for weak and strong coupling, respectively. In the presence of noise, the probability distributions for the Henon map network also exhibit bimodal behavior, with 2 regions of high probability for chimera observation. The modified Ricker map network introduces a new regime solitary states which are characterized by regular dynamics in time with periods t=4, t=8, and t greater than 8 for weak coupling, and t=3 and t=6 for strong coupling. The transition from solitary states to chimera states occurs as the coupling strength increases, and both regimes can coexist temporarily. The probability distributions for the Ricker map network in the presence of noise are also bimodal, with 2 regions of high probability for chimera observation. The findings of this study demonstrate that chimera resonance is a universal phenomenon that can be observed in various networks of non-locally coupled chaotic maps. The specific characteristics of the probability distributions and the emergence of solitary states in the Ricker map network underscore the importance of considering the local dynamics parameter and the coupling strength in understanding the complex interplay between coherence and incoherence in these systems. The study explores the impact of additive Gaussian noise on spatio-temporal dynamics and the probability of observing chimera states in 3 different ring networks of non-locally coupled chaotic discrete time systems. These networks are composed of individual nodes described by the logistic map, modified Ricker map, and Henon map. In the noise-free networks, 2-dimensional diagrams of spatio-temporal regimes were constructed in the local dynamics parameter versus coupling strength parameter plane. The analysis reveals a coherent window inside the region with profile discontinuities in the diagrams of dynamical regimes, which significantly affects the probability of observing chimera states in the presence of noise. To understand the role of additive noise, two-dimensional distribution diagrams for the probability of chimera existence were plotted in terms of the coupling strength sigma and the noise intensity d. The numerical simulations show that in the presence of noise of certain intensities, chimera states can be induced in the networks studied and the probability of their observation can be significantly increased up to its maximum level, equal to 1, within a specific range of the coupling strength and noise intensity. For the modified Ricker map network, the existence of solitary states within a narrow region in the alpha r sigma parameter plane for strong coupling leads to a distinct distribution of the probability of observing chimera states in the sigma d parameter plane. The presence of additive noise influences the network dynamics and the probability of chimera states, depending on the initial regime. In the case of snapshots with profiled discontinuities, a low noise intensity leads to the appearance of phase chimeras with narrow incoherent clusters. An increase in noise intensity first leads to entering into the region with zero probability of observing chimeras, where incoherent dynamics occurs in the network, and then again to the existence of chimera states at a sufficiently high noise level. In the solitary state regime, a gradual increase in the noise intensity initially has almost no effect on the regime in the network, with the number of solitary nodes varying slightly. As the noise level increases, solitary nodes disappear and the network dynamics is characterized by a snapshot with profiled discontinuities or by phase chimeras with narrow incoherent clusters. A further increase in the noise intensity leads to entering into the region with zero probability of observing chimeras, where incoherent dynamics occurs in the network, and then again to the existence of chimera states at a sufficiently high noise level. The research discusses chimera resonance in networks of chaotic maps, focusing on the interplay between noise, coupling strength, and local dynamics parameters. It highlights the existence of a higher maximum probability of observing chimeras within a specific region of the coupling strength and noise intensity. This phenomenon is attributed to the presence of a coherent window in the network dynamics, which is influenced by the local dynamics parameter. The study also explores the role of noise in enhancing the probability of chimera observation, particularly at a certain, resonant, value of the coupling strength. The results demonstrate the constructive role of noise in the dynamics of complex networks, offering insights into the control of spatio-temporal structures. The research further discusses the impact of noise on the amplitude chimera lifetime and the effect of multiplexing noise on interlayer synchronization. The findings have implications for understanding and controlling complex systems, particularly in the context of synchronization and desynchronization phenomena. In the realm of complex systems, chimera states have garnered significant attention due to their intriguing properties, which involve coexistence of synchronized and incoherent oscillations within a single network. These phenomena are observed in various fields, including physics, chemistry, biology, and neuroscience. The concept of chimera states was first introduced by Kuramoto and Batogtok in 2002, who demonstrated that such states could emerge in a ring of non-locally coupled phase oscillators. Since then, numerous studies have been conducted on the subject, exploring different types of chimera states, such as amplitude chimeras, weak chimeras, and solitary states. One notable study by Hagerstrom et al. 2012 explored the existence of chimera states in networks of coupled chaotic maps, using the logistic map as an example. This work showed that chimera states can be induced through non-local coupling and demonstrated the robustness of these states against external noise. Further research by Omelchenko et al. 2013 investigated the stability and bifurcations of chimera states in networks of coupled chaotic maps, revealing the importance of the interplay between local and non-local interactions. Moreover, the study by Mikhailenko et al. 2019 shed light on the role of delay in enhancing the stability of solitary states in complex networks, highlighting the potential for adaptive control strategies to manipulate network behavior. In addition to theoretical investigations, experimental studies have also been conducted to validate the existence of chimera states. For instance, Gambutsa et al. 2014 demonstrated the presence of chimera states in electronic oscillator networks, while Hellman et al. 2020 observed these states in a power grid system. Moreover, chimera states have implications for real-world applications, particularly in the context of power grids. Taher et al. 2019, proposed a time-delayed feedback control method to enhance synchronization and stability in power grids, leveraging the concept of chimera states. Similarly, Berner et al. 2021 utilized adaptive neuronal networks to improve power grid synchronization and stability, drawing parallels between the two systems. In conclusion, the study of chimera states continues to be an active area of research, with ongoing investigations into their stability, bifurcations, and potential applications in various fields. The interplay between local and non-local interactions, along with the role of delay and adaptive control strategies, are key aspects that have garnered considerable attention. As researchers delve deeper into the complexities of these phenomena, they continue to uncover novel insights and possibilities for manipulating network behavior.